So before we move into metric spaces, we are going to take a slight digression, which I feel is necessary. We are going to look at what are called vector spaces. If you have taken linear algebra, you might be familiar with the concept of vector spaces, but we are going to look at something called normed vector spaces, which will ease us into metric spaces in a way. Okay, so if you haven't taken linear algebra or if you have forgotten what a vector space is, this is the definition. Definition: let F be a field. Let F be a field. And a vector space over F. A vector space V over F is a set V consisting of elements called vectors, consisting of elements called vectors together with two operations. Together with two operations. Two operations. First, vector addition. Vector addition. V cross V to V, denoted by plus, and scalar multiplication, which is multiplication of a vector and a scalar, which goes from, by convention, F cross V to V, okay, denoted by generally juxtaposition, which is i.e. just alpha times alpha v for alpha belonging to F and V belonging to V. We generally do not put a dot or a cross to denote this multiplication because both of these symbols have very specific meaning. Okay, so these are both avoided. You just write them together to denote multiplication. Okay, these operations satisfy the vector space axioms. Vector space axioms. Well, these operations should satisfy, should satisfy the vector space axioms. Okay, let me just do this. Operations should satisfy the vector space axioms, which are, first, the vector addition is commutative and associative. Vector addition is commutative and associative. I am not going to elaborate on what that means. You should know the definition of these words by now. Second, V contains an additive identity. V contains an additive identity called zero vector, called the zero vector, denoted 0, such that 0 plus V is equal to V plus 0 is equal to V for every V belonging to V. Okay, so technically this part, that V plus 0 is equal to 0 plus V, is guaranteed by commutativity. I just like to write it in any case either. Every element has an additive inverse. Every element has an additive, element V has an additive inverse negative V, such that V plus negative V is equal to 0. 4. Multiplication by scalar is compatible with multiplication in F. Multiplication by scalars is compatible with multiplication in F. With multiplication in F, i.e. alpha times beta V should be equal to alpha beta times V for every alpha comma beta in F and V in V. Okay. Fifth, if one denotes the multiplicative identity in F, if one denotes the multiplicative identity in F, then 1V is equal to V for every V belonging to V. Okay. Technically, this is a direct consequence of multiplication by scalars. You get that 1V times 1 is equal to 1 times V, and so things are being preserved. But it is always important to write it out explicitly. This is an important property that should hold true. And the following distributive law holds. The following distributive law holds, which is for every alpha comma beta belonging to F, V belonging to V, UV belonging to V, we should have that alpha times U plus V is equal to alpha U plus alpha V, and alpha plus beta times V is equal to alpha V plus beta V. Okay, now note this is the reason I mentioned distributive law completely, rather than just saying, oh, distributive law should hold. This is because the addition on the left-hand side is in F. Note, addition on LHS is in F, while addition in LHS is in F, while in RHS, while addition in RHS is in V. We are abusing notation by denoting both of them by the same symbol. Abusing notation by denoting both with the same symbol. Okay, technically these two are very, very different operations. One is technically not defined on the other, but since they are defined in their usual ways in the respective places, we are going to say, oh, you know what I mean when I say alpha plus beta. Of course it happens in F. You know what I mean when I say alpha V plus beta V. Of course it happens in W. It makes sense. V. If it makes sense in V, it makes sense in alpha in F. So I'm just going to say, let me just use this symbol. Okay. An R vector space is a vector space over reals, is a vector space over reals. Similarly, a C vector space is a vector space over complex numbers. A subspace definition, definition, a subspace W, a subspace W of a vector space V, is a vector is a subset of V, which is an F vector space in its own right. In its own right, with the same operations as F. With the same operations as in V, not F, sorry. Okay? What that means is you're looking at it as a subspace, and you should be able to use the operations of V on this subspace, and they should make sense. Things should be closed under addition, vector multiplication, not vector multiplication, scalar multiplication, and everything. Okay, let us look at some examples. First, for any field F, let me just do this. Let F be any field. Let F be a field. The following are vector spaces. The following are examples of vector spaces. Okay. Oftentimes, vector spaces will be denoted just v dot s dot. Okay. F itself, first of all, is a vector space. F is a F vector space. F vector space. Okay. In this case, the vector space operations. In this case, the vector space operations. The vector space operations are the same as operations on F. Keep in mind, vector spaces do not have multiplicative inverses, okay? Because you can't multiply vectors by vectors by we have no multiplication as of now defined between vectors, right? So there's no sense of saying inverse of a vector, okay? A multiplicative inverse of a vector, okay? Now, f to the n can be made into a vector space, can be made into a vector space with component-wise with component-wise addition and scalar multiplication. Scalar multiplication. Okay, what does that mean? Alpha 1, alpha 2, dot dot dot, alpha n plus beta 1, beta 2, dot dot dot, beta n is equal to, actually let me just combine the two. This is equal to alpha 1 plus lambda times beta 1 dot 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 alpha 1 alpha n plus lambda times beta n. Okay, i.e. for every alpha I, beta I, comma lambda belonging to f, this should hold. Okay, the zero element is just 0 0 dot 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 0. Okay, third, now this is a very peculiar case. Okay, for any set x, the space of functions, well, the set of functions, f to the x, right, let me just say this, the set f to the x of functions from x to f can be made into a vector space. Can be made into a vector space. Okay. Now, a very special note that I'm not going to write down, but the previous example, example 2, is a very special case of example 3. Okay. In that case, my set x is just 1 to n. Okay, so Jn with prior notation. But it is an important enough case. We are more likely to deal with Fn than f to the x for random sets, so we are denoting that specially. We are mentioning that separately. So how is this a vector space? Given functions f and g, given functions f, comma g, which are from x to f, from x to f, and alpha belonging to f, we define alpha belonging to f, define the addition f plus g and alpha x and the scalar multiplication alpha f to be as follows. To be as follows. F plus g of x is equal to f of x plus g of x, and f times g, so not f times g, alpha f of x is equal to alpha times f of x. Okay, for every x. For every x in x. For every x in x. Okay. Once again, this definition is now in the vector space. Okay. The addition f plus g is happening in the vector space, while this addition here is happening in the field. Okay? But this makes sense. Okay? Okay, so this is what a vector space is. Now, what is a normed vector space? Normed vector space. Okay, what is a normed vector space? Definition. Let V be a vector space. V be a real vector space. Let V be a real vector space. A norm on V, a norm on V is a function generally denoted this way, double bar on both sides. The dot has no special meaning, it's just a placeholder since we don't want to use x or something. So this is the standard notation of norm. So absolute value is denoted by single vertical bar on both sides. Norm is denoted by double vertical bar. From V to R. Okay, satisfying the following properties. Satisfying the following properties. First, non-negativity. Non-negativity. V norm of v is greater than or equal to 0, and norm of v is equal to 0 if and only if v is equal to 0. Okay? For every v belonging to v. Second, homogeneity. Homogeneity. What does this mean? Norm of alpha v should be equal to absolute value of alpha times norm of v for every alpha belonging to R and v belonging to v. Okay. And third, what is a very special property which will be used always, the triangle inequality. Triangle inequality. What is triangle inequality? The norm of u plus v should be smaller than or equal to norm of u plus the norm of v for every u comma v belonging to v. Okay? Such a vector space is generally defined such a normed vector space is generally denoted v, comma, the norm. Okay? So, examples? Super done. Just a note, you can replace some of these things. You don't need to work with R. You can work with, for example, Q, right? Any ordered field where you have some sort of idea of what positive means can be used. In our case, we are going to deal with R, but you can use other fields also. So first, R itself is a real normed vector space with absolute value. R is a real normed vector space with absolute value serving as the norm. Right? You can easily check that all three of these hold true for R. Now, R to the n is a real normed vector space. Real normed vector space with the Euclidean norm. Which is norm of x1 dot 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 xn is equal to square root of x1 squared plus x2 squared plus dot 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 xn squared. You have used this to define distance on R2. This is how you find distances in R2, right? This is exactly how you generalize it to R3, Rn. So this is a real normed vector space. Okay? And you will have to show that triangle inequality holds for it. but it can be shown. There are easier ways to show it, and we'll show it later. 3. If I don't show it, I'll ask you to show it as a homework exercise, but I will show you something stronger that makes it easier. You don't have to go through the entire calculation that way. Okay? Now, the problem is we can't make R to the X a real normed vector space for general sets X. Real normed vector space for general sets X. Okay? Why? Why can't we do it? I want you to think about this. I will give you a hint. What happens? Why can't we use the why can't we use norm from 2 if X is infinite set? I want you to think about it. It's not anything super hard, but think about what can go wrong when you're trying to use the norm that you have in the previous one. Okay? Take a vector which is maybe 1 in each coordinate and tell me what its norm would be. Okay? So think about it. That should give you the answer. Okay? However, we can define a norm on the subspace of bounded functions. Define norm on subspace of bounded functions, which we will generally denote Bx. Okay? What is a bounded function? Bx, a function f of x is bounded if f of x is smaller than, if f of x is smaller than a certain n for every x, right? What is the norm? The supremum norm, or the sup norm for short, also called the uniform norm, is defined by norm f, which is generally denoted U for uniform norm, is supremum x belonging to x absolute value of f of x. Okay? Homework. Prove this is a norm. Prove this is a norm. That is, you want to show that it satisfies all the properties of a norm. Okay? And for it, as a special case of previous, as a special case of 2 and 3, we can put a uniform norm. We can define uniform norm on Rn. Okay? And the uniform norm is just the uniform norm of X is equal to maximum of x1 all the way up to xn. Okay. Now, let me introduce you to how multiplication can be defined on vector spaces. This is something that you might have seen before in Calculus 3 or Calculus 4 if you took it. But here's what we have as multiplication. Real inner product spaces. Inner product spaces. Definition. An inner product on a vector space V, and inner product on a vector space V, on a real vector space V, on a real vector space V is a function which is defined dot comma dot. Okay, where again the dots are just placeholders from V cross V to R, which satisfies three properties, which satisfies the following. First, symmetry. This one symmetry, which says the inner product of x and y should be equal to the inner product of y and x. Of y and x for every x comma y belonging to V. Second, linearity in the first component. Linearity in first component. Okay. Which is to say, lambda x plus y comma z should be equal to lambda of lambda times x comma z plus y comma z. Okay, for every x comma y comma z in f, in V. I'm not going to write that. Well, x, y, z have to be in V and lambda has to be in f. Third, positive definiteness. Positive definiteness. Okay, what does that mean? X comma x is greater than or equal to 0 for every x belonging to V, with x comma x is equal to 0 if and only if x is equal to 0. Okay, 0 vector. Okay, in this case, this is called a real inner product space. Note, linearity in first component, linearity in first component or first component automatically implies linearity in second component, linearity in second component for real inner products, for real inner products. Okay. There's a reason why I'm saying in real inner products. You can define inner product on complex vector spaces. We can define inner product on complex spaces, complex vector spaces, but then the symmetry condition becomes different. However, symmetry condition then becomes the complex conjugate conditions becomes conjugate symmetry, which is to say x comma y is equal to the conjugate of y comma x. Okay, and this also affects the linearity in second coordinate. Okay, so linearity in first coordinate would still be as usual. Linearity in second coordinate gets affected by the conjugate condition because linearity in second coordinate follows from symmetry and first coordinate. Okay. Example. First, the dot product on Rn is an inner product. If you remember what dot product is, the dot product of x is equal to x1, x2, dot, 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 xn, and y is equal to y1, y2, dot, 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 yn is then x dot y is equal to x1 y1 plus x2 y2 plus dot 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 xn yn. Okay, this is the definition. You might have seen this before. Note then that the norm of x, the standard norm, well, let me just say, then x dot x is just x1 squared plus x2 squared plus dot 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 plus xn squared, which is equal to norm of x squared. Right? You have seen this before. And we will show using the coming theorem that this would imply that this is a norm. The norm satisfies triangle inequalities and everything. Okay. So this is one example. Okay, fine. I didn't want to. I was wondering whether we should do it. The integral is an inner product on certain class of functions. Is an inner product on certain functions. Okay. I won't go into details of what the certain functions are, because it will take too long. This is not something. This is just a rough example that I want to give, because integral of f g dx is equal to integral g f dx, as long as your functions are nice. Okay, as long as functions are okay. Let me not even say this. Okay, this is true, and integral of lambda f plus g dx is equal to lambda integral of f dx plus integral g dx, and integral f dx is equal to integral of absolute value of f squared dx, which is always greater than or equal to 0 because it's a positive function. Okay, why are we saying on certain functions? The idea is, if you have taken calculus, you know that not all functions are integrable. You need your function to be integrable. You want your integral to be defined. You need it to be finite. All of these things to have need to hold true. If you're dealing with functions whose integral is finite, then this is an inner product on those functions. Okay. Otherwise, forget about it. It was just an example. Then we come to theorem 1. Let V be a real vector space. Let V be a real vector space. And let the inner product be an inner product on V. Be an inner product on V. Then any norm which we define on V by square root of dot comma dot is a norm on V, is a norm on V. Okay? We are not going to instantly prove this. We will prove this by a series of results. So the proof is not going to be one step. We are going to go through a number of steps, and that will eventually give us the proof. Okay? This will also imply that the norm that we did before, which is our standard Euclidean norm, is actually a norm. Okay? First step, definition. Let V be a vector. Let V be an inner product space. An inner product space with inner product dot dot. Okay, and let U comma V belong to V. Okay, we say U comma V, U and V are orthogonal. U and V are orthogonal if their inner product is 0. If U comma V, the inner product of U comma V is 0. Okay. There's a small note to be mentioned. This definition means the zero vector is orthogonal to everything. Okay, the inner product of zero with anything is always zero, and so it is orthogonal to every other vector. Then theorem 2, the Pythagorean theorem for real inner products. Pythagorean theorem for real inner products. Okay, you know the Pythagorean theorem that you have studied before. This is a generalization of that, which says let V be a real inner product space, be a real inner product space with dot dot, and let U comma V belonging to V be orthogonal. Be orthogonal. Okay. Then norm of U plus V squared is equal to norm of U squared plus norm of V squared. Okay. This is literally the Pythagoras identity if you look at norm as just the distance, and these are sides of a triangle. If they are sides of a triangle by orthogonal, it would mean that they are perpendicular to each other. So you're looking at a right angle triangle, in which case, if you look at vectors, if you look at U and V as vectors, U plus V is going to be the hypotenuse of the right angle triangle. Proof, expand U plus V squared, which is what? Well, U plus V squared is by definition U plus V inner product with U plus V, which upon expansion is U comma U plus U comma V plus V comma U plus V comma V, right? And because these are orthogonal, these two are 0, is equal to 0, is equal to 0. So I get UU, which is just norm of U squared, plus VV, which is just norm of V squared. Okay, and that's the simple proof. Then proposition. So let me just say this is proposition 3. Let me go on with proposition. Existence of orthogonal projections. Existence of orthogonal projections. Okay. Let V be a real vector space with inner product. Let V be a real vector space with inner product dot comma dot, and U comma V belong to V. Okay, not necessarily orthogonal. There exists a number C. There exists. Okay, let me not do this. There exists a number C. Number C, a real number C, and a vector Z such that Z is such that U is equal to CV plus Z and V comma Z, the inner product of V comma Z is equal to 0. That is to say, Z is orthogonal to V. The number C is given by C is equal to U tensor U inner product V over V squared. Okay. The vector CV is called the orthogonal projection of U onto V. The vector CV is called the orthogonal projection of U onto V. Okay? If you want to have a mental image of what is going on, okay? So, mental image. Think about it as a vector U, a vector V, U, and then the orthogonal projection is this. This vector here is CV. Okay? So that is what is going on. Proof. Define C as we did it before, as we are told. Define C is equal to U tensor V over absolute value of V squared. This is a real number. And define Z is equal to U minus CV. Okay? Then what should hold true? Well, CV is the orthogonal, is the parallel part of V, of U, and whatever is left, so this is going to be my Z. Okay? I just want to show the product of Z comma V, or as we said, V comma Z. V comma Z is what we mentioned. So let me go with V comma Z. V comma Z is equal to, well, V comma U minus C times V comma V, right? Inner product of V comma V, which is equal to V comma U minus U comma V. Well, let me write it down on the next line. Is equal to, well, V comma U by symmetry is U comma V. So let me write U comma V minus C times, well, C is what? UV over norm of V squared, and VV is just norm of V squared. Right? Is equal to 0. And thus, V and Z are orthogonal as needed. Okay, and that brings us to the most important theorem here. Theorem 4, which is the Cauchy-Schwarz inequality. Cauchy-Schwarz, H-W-A-R-D-Z, inequality. This is a very powerful inequality which is used extremely commonly. This is going to be the bread and butter for all norm calculations. This is going to be popping up so much everywhere. Cauchy has a lot of work. Cauchy did so much work for analysis, especially complex analysis, that nearly every single theorem that you'll see in complex analysis, you can add Cauchy to it, and everyone will be like, yeah, that is, yes, that theorem is by Cauchy. Every single theorem is by Cauchy. Cauchy has contributed to every single theorem there. And Cauchy-Schwarz inequality is some of his more easily accessible stuff. What does it say? If ... is an inner product on a vector space V, is an inner product on a real vector space V, then the absolute value of U inner product V is smaller than or equal to norm of U multiplied by norm of V. Okay? For every U comma V belonging to V. Okay? It's pretty easy to define proof. The idea is going to be to use orthogonal projections. So let C is equal to UV over V squared, norm of V squared, and let V squared and let Z be V minus U minus CV is equal to U minus CV. Okay, which is then from previous proposition orthogonal to V. Okay, then by Pythagorean theorem, Pythagorean theorem of CV and Z, we get that U squared is equal to CV plus Z squared, right? Because CV plus Z is just U, is equal to, well, CV squared plus Z squared, because these are orthogonal to each other, right? And this is greater than or equal to C times norm of V squared plus 0, right? Well, what is norm of C? Norm of C squared, V squared times 0. What is norm of C? C is U tensor V squared over V squared. So this becomes norm of U comma V squared all over v norm of v squared, so squared, so that becomes to the fourth, times norm of v squared, which is equal to inner product of uv squared over v squared, right? And therefore cross multiplying, therefore u squared multiplied by v squared is greater than or equal to u comma v squared. Okay, proving the inequality. And now we can finally prove theorem 1. Okay, theorem 1, proof of theorem 1, proof of theorem 1. Well, now that we have this, it's pretty easy. Just expand absolute value of u plus v squared, expand u plus v squared. Well, what is this? U plus v squared is by definition again u plus v, which is equal to u plus 2 uv plus vv, which is what? U is u squared plus v squared, right? Plus 2 uv. Well, now this is smaller than or equal to, if I take square root of both sides on this inequality right here, if I take square root of that, I get u squared plus v squared plus 2 u v, well, which is exactly equal to u plus v whole squared, right? Now taking the square root on both sides, taking square root of both sides. Taking square root of both sides just gives me, therefore, norm of u plus v smaller than or equal to u plus v. Okay, and that proves the triangle inequality. Proves the triangle inequality. Okay. Homework. Show the rest. Show the rest. This is the only complicated step. The other two are really easy. We have shown this. Prove the rest. Okay. Let me stop this video here. We are now done with normed vector spaces, and we'll use this to prove the properties of metric spaces next time. Okay.